All right, good afternoon, everybody. The purpose of this video here is to help you with problems 8 and 9 on the worksheet called Power and Energy Dissipated by a Resistor. Kind of a lot going on there with 8 and 9, so I want to take some time here and walk you through that. So, number 8, if you notice there, I have number 3 on the board as well. I'll explain why here in a second. Number 8 from the worksheet itself says the electric space heater in problem 3 runs for 5 hours a day. So you need to know how much power is used in running that space heater. So that's why number 3 is up here. Now, if you look at number 3 for a second, it says nothing about the resistor dissipating any power or energy. So we're just going to use the basic, what I call the basic power formula, P equals I times V. So we know the amps, the current is 13. We know the voltage is 120. Plug it in your standard wall outlet. 13 times 120 is 1,560. So we need that bit of information to help us with number 8. Now, that being said, see, the electric companies, they measure the amount of power that is used by consumers in kilowatt hours rather than just watts, because it's just easier. It's an easier calculation for them. It'd be like measuring the distance from here at CTEC to let's say Johnstown and reporting that measurement in centimeters. All right, it'd be a pretty large number. Where we deal with miles and kilometers and that, mostly miles. So that's a little bit more what we're used to. It's a little bit more. It's easier to work with. So 1,560 watts is equal to 1.56 kilowatts. All right, divide by 1,000, and you get 1.56. Now the question is, how much energy in kilowatt hours does the space heater consume in 30 days? So now I'm looking at question part A under number 8. So we're talking about calculating the amount of energy, so I'm going to use this formula. Let me put a black marker, it'd be easier, I think. E equals P times T. All right. Now, from number 3, the power is 1.56 kilowatts. All right. How many hours is it running a day, the space heater? 5 hours. So we're going to multiply that by 5. All right. 5 hours a day. And this is going to tell us how much energy in kilowatt hours does it use. Well, not quite. Once we multiply this is the amount of energy it's using in one day. 7.8 kilowatts per day. Then you're going to multiply 7.8 times 30 because there's 30 days in the month. Not all months have that, I know, but that's just what we're going with. So 7.8 times 30 is 234 kilowatt hours. All right, 234 kilowatt hours. So that's the answer to part A. All right, 234 kilowatt hours. Here's the answer. All right, so again, we had the power. We know we're running for 5 hours a day. This is how many kilowatt hours it's using in a day. There's 30 days in the month, so 7.8 times 30, 234 kilowatt hours. Now, for part B, we're going to take this answer, because this is the amount of energy it's using in a month. We want to know, okay, at 12 cents a kilowatt hour, how much does it cost to operate the heater for 30 days? So we are going to take 0.12, in other words 12 cents, and we're going to multiply that by 234 kilowatt hours, and we are going to come out with a dollar amount of $28.08. All right, so this is how much it costs the consumer, you the consumer, to operate that space heater for 5 hours a day for 30 days in the month. All right, it's going to cost you $28.08. Now, all right, so number 8 here, it's just based on understand what a kilowatt hour is, which is, again, that's the way that the power companies, it's a basic way for them to measure the amount of electricity that is being used by a consumer. All right, so we got $28.08 there for part B. All right, so that's number 8. Now, number 9. Number 9 says, and you got your copy there. A digital clock has a resistance of 13,000 ohms. All right, and it's plugged into a 115 volt outlet. All right, so we know we got the resistance, we got the voltage. Part A, how much current does it draw? All right, so what we're going to do is we're going to use Ohm's law. R equals V over I. And we're going to say 13,000 equals 115 over I. All I did was, I know my resistance, I know my voltage, I just plugged those numbers in the respective locations in the Ohm's law formula. What you're going to end up doing here is dividing 115 by 13,000. So yes, you're going to end up with a really small number. In fact, that number looks like this. So again, 115 divided by 13,000, 0.0088 amps. Okay? All we did there was use Ohm's law. Now, in part B, it says how much power does it use? All right? Well, it doesn't say about the power being dissipated by the resistor, even though we're talking about, we have a value here of a resistance of 13,000 ohms. That's fine. We're going to end up using this equation here, P equals I times V. All right, your basic power equation that I addressed in number 3 a little bit earlier. Now, we know the current is this, so take 0.0088, okay, and we're going to multiply that by the voltage, which we also know is 115. Now, on the document, it says express your answer in kilowatts. So once we multiply this, let me grab the calculator because I'm sorry, I don't know this off the top of my head. All right, so we're going to say 0.0088 times 115, and we get this, 1.018. Actually, I think that comes out to 2 because this, I took it out to 4.6, but it's fine. It's fine. All right, so just 4.6, sorry about that. So 0.008846 times 115 gives you 1.018. All right, and that's in watts. Now, you want to convert this to kilowatts, so we're going to divide by 1,000, and we're going to get 0.00, make sure I got the right zeros here, 1018 kilowatts. All right, that's your answer to part B. All right, 0.001018 kilowatts. Then for part C, to kind of finish this off, it asks you at 12 cents per kilowatt hour, how much does it cost to operate the clock continuously for 30 days? All right, so there's no power interruptions, nothing like that. So we're going to take this answer here in kilowatts because the units are in kilowatts. And I apologize for you having to see my back here for a second, but that's nothing we can really do about that. And this is again times 12 cents per kilowatt hour. All right, it's running for 24 hours and 30 days. All right. So here's kilowatt hours. Here's the hour converting to hours, then converting to days. Because that's how the power company does this. When you multiply these numbers together, all these numbers, you get 0.087. All right, this is a monetary amount. So it's like, 8 cents and 7 tenths. Well, we just rounded up to 9 cents. All right, so this is just 9 cents. All right, and that's how you handle part C. All right, so for number 9 is independent of number 8. But just give you, a little bit more practice with using Ohm's law, and we had to figure out what the current was. All right, based on Ohm's law, we know from the problem that the resistance is 13,000 ohms. The voltage is 115, so we plug those numbers again into the appropriate locations for the equation. Divide it out, we get this tiny number here. Then for part B, P equals I times V, so it's over here. Here's your current, here's your voltage. Multiply the two out, and then this is watts. We convert it to kilowatts, because again, that's what the power companies use. All right, then we took that answer, brought it down here for part C, and said 0.001018 times 12 cents per kilowatt hour, running continuously for 24 hours, 30 days in the month. So if you want to save yourself 9 cents, unplug that digital alarm clock. All right, that's what we need to do there. Now, rest assured that will you see something like 8 and 9 on the test? No. Okay. This is in here just to basically challenge you a little bit, but I don't want you to lose your mind over this either. So you have now you have 8 and 9 solution there. So if you get stuck with that, know that there's a video that it's going to be posted here in Classroom in a little bit that will help you with numbers 8 and number 9. And if you have questions, let me know. And so good luck with that, and we'll see you next time.